Good afternoon all. Today we have reached to the 5th day AICTE ATAL-FDP program. I, Dr. Sneha Sultana, on behalf of Dr. BCREC Engineering College Electrical Engineering Department, welcome you all. Today as eminent speaker we have Dr. Karabi Biswas, Professor, Department of Electrical Engineering, IIT Kharagpur. May I have the honor to read her biodata. Dr. Karabi Biswas received the B.Tech degree from the Indian Institute of Technology, Kharagpur, India in 1992. The M.Tech degree from Durgapur University in 2000 and the PhD degree from IIT Kharagpur in 2007. As a member of the Sensor Development Research Group, she currently serves as a professor in the Department of Electrical Engineering, IIT Kharagpur. Her research interests include sensor development, instrument system design, and study of fractional order system. Dr. Biswas is one of the pioneers in developing a fractional order element which can be used as a low-cost device in an electrical circuit. Her research on fractional order element now extends to the analysis of origination of its fractional order behavior, customization, and packaging. Dr. Biswas was the recipient of AICTE Career Award for Young Teacher in 2007 to 2008, Boys Cast Fellow and Dad Visiting Researcher, Saarland University, Germany in 2009 and 2012 respectively. Friedrich Wilhelm Bessel Research Award from Leibniz University of Hanover, Germany in 2022. Dr. Biswas is an associate editor of International Journal of Circuit Theory and Application and IEEE Sensor Journal, a review editor for Frontiers in Electronics, and has served as a guest editor for special issue in Fractal and Fractional. She is a member of IEEE, USA System Society of India, and the Indian Dairy Association. Thank you, ma'am. Please.
Thank you for the nice introduction. I think, do I need mic or I am audible? Audible. I am audible. Then I think mic is not required. That recording will be a problem? Otherwise, I will go without mic. Is it okay, or should I go with the mic?
Okay.
No problem. So if you prefer, I can go with the mic also.
Volume master to?
So it's fine, right? No. Okay. So, I was actually, Shivendu was my student when I was in Durgapur University. Actually, I was a faculty in Durgapur University. Then I joined IIT Kharagpur, and I think as I got the information from you, and also I can recall that I have given 2 more invited lectures here on some other program. One, I think, in automotive sensors, and one was fractional order element. Okay, I think in the fractional order element, which the previous one, that I mostly concentrated as a circuit element. So here I will be mainly talking about the sensing part of it. It's like a capacitor, right? So you can use it as a circuit element in electrical circuits, or you can use it as also as a capacitive type sensors. So let us see that how this can be used as a sensor, and whenever there is anything that I am unable to communicate you, please raise your hand. We all are teachers, teaching the class, so that is okay. There is no problem, right? So please raise your hand if you have any query. I will stop. Try my best to. So my presentation summary will go like this. Just I will give a little introduction about the fractional order element. I think most of you know because one of your teacher works in this domain, and I really appreciate him that the good work he has done staying in this Dr. BCREC Engineering College. I really feel proud of that also, and take a little bit pride that he was our student. Okay, so today that small part will be the fractional order element. Then actually this we have used in different sensing, which I have listed. So the monitor, the batch yeast culture, the detection of spoilage of milk. Actually this I have done during my PhD itself. And the detection of adulterated in milk, actually one of my PhD student in Durgapur University, and later again one student in Kharagpur that continued. Still I work on this same area, that now trying to build a prototype which can be commercially viable. So adulteration milk is one of the application that I have found is very suitable for the census. And with some master student, I have also done some measurement of mammalian cell concentration. So as when you first time see some census, so always you have this temptation, so let me see that where it can be applied. So similarly with the sensor, I went to the biotechnology department of IIT Kharagpur, and they said, okay, why not? So what they see under the microscope, so I thought, let me see that whether I can just dip in that mammalian cell culture and whether I can measure the concentration of cells. So that we have done. Then actually now we have actually developed a conductivity meter. pH meter development is still under progress with the same sensor principle. And we have a project for this detection of mastitis disease in cow, that mastitis detector actually, that is we are doing with the collaboration of CDAC Kolkata and the National Dairy Research Institute Kolkata. So that is also a product which I hope will be successful. And then I will try to discuss some future scope of these sensors. So I think as Shivandu works actively in this area, many of you know this, that what is a fractional order element. So this those who work in this domain, we say that it is actually the generalization of the circuit element. So you can see the equation, Zs equal to Qs to the power minus alpha. So I have this alpha of any value, even the complex number. Now you will be knowing that many people are trying to develop controller. I think those who works in control, in fraction control, this Crone controller, the first generation, second generation, they were actually use the fractional order real, but in the third generation Crone controller, they are taking this alpha as a complex number. So that's why it is a generalization of the circuit element. That means alpha can be anything. So what we have in our lab, every day we use, that is resistor, capacitor and inductor. We call it, that is a only for a particular special cases. When alpha is 0 is resistor, 1 is a capacitor, minus 1 is a inductor. And when actually at the beginning we limited it to the alpha to minus 1 to 1 because actually we could realize this alpha value between this value. So we call this a fractional arrangement. So actually how it is evident. So here I would like to say that actually this whole research actually started from the experimental observation. So we found that when I was dipping a typical particular type of probe in a polarizable media, then it is showing me the phase angle which is neither 0 degree, not 90 degree or minus 90 degree. So something in between, actually from 0 to minus 90 it was minus 45, minus 60, minus 32. So then that time we were very excited, me and my supervisor, that maybe we have found something new. But then we searched the literature and see that in 1695, when Leibniz and Newton, they were actually developing calculus, then Leibniz actually had posed this question that we are non-integer, then what will be the consequence? So that means it was in someone's mind in 1695. So that time, after that you will see in mathematics there are lots of work has been done on fractional calculus. Many people have Euler, this Riemann-Leveley, Caputo. So they have developed a systematic this how to deal with the parallel branch of calculus. Like we learned that integer order calculus, but that is fractional calculus. And if you see that now fractional calculus, you can say that why that is important. Nowadays when we see that there is so much of complexity in nature, if you want to capture that, then actually the integer order calculus is not sufficient. We need to make it go to the fractional domain. On simple example, we can say that suppose a micro positioning or the robots. Now the soft robots you might have learned. So they are actually the control, how to control that path. So if you use the integer order control or loop shaping method, that may be a problem. But if you adopt a fractional order controller, that may be very obvious. The reason is your system, that soft robotic, it has very small parts connected. Itself, that system is a fractional order system. So if a system is fractional order, its control also, if it is in the fractional, then you can make the controller, best controller out of it. Right? That is the control theory says. So that's why when we developed the element, we found that it is actually an element which has many prospects, and we have identified in this domain. Now many people are trying to get a fractional inductors also. Actually in our lab, by experimenting again, actually when I was making the fractional capacitor, I heated that dielectric, actually we modulate the dielectric in between the electrodes to get the capacitors. So when it was heated above a temperature 60 degree, then I found it was behaving like a fractional inductor. But unfortunately, after 3 months, it lost its behavior, and that was a transient state. So people are trying to develop this fractional inductor. That is, if you search literature, you will see in the across the globe, many people are devoting time on that also. So I can say here that one of these research area of fractional order element, you can say that see we have resistors in this coordinator, we have inductor in this coordinator, we have capacitor in this coordinator, and we call it the negative resistance. But any element in between is actually a fractional order element. Now you can say if my life is simple and okay with the resistor, capacitor, inductor or negative resistance, why should I take the extra burden of this fractional capacitor? So here you can see this impedance plot. So you know when we make a resonator in electrical circuit, then what is the Q factor on the denominator? The R comes, right? Omega L by R, 1 by omega CR, and that R is actually creates the problem. It flattens your Q. So when you want to make a selective this frequency or resonator, then you want to, ideally you want to make R equal to 0. So if you have an element in this coordinate, so see it has a component across this, it has a component across this. So if you have a R in your circuit, so the component which is across this, that you can nullify this resistance, and here this actually getting added up. What does it mean? Your Q factor is becoming very sharp. So that we also have seen that we can theoretically it can give infinite, but practically of course there are some issues. So we got actually the notch filter and the fractional filter that is really very high Q, which is not actually achievable by the integer order elements. So that is one of the research area, and people are exploiting this behavior of the fractional order element. So it is also, I think, very obvious that if I have this fractional order element, I define like this, then I have an omega, that means in frequency domain, I can represent it as Z j omega equal to Q, j omega to the power minus alpha, and its magnitude is Q omega to the power minus alpha, whereas its phase angle is minus pi alpha by 2. That's why actually in the previous slide you see we are getting different values of phase angle, because you can see here my phase angle is pi alpha by 2. So alpha by 2 is 90 degree, if alpha is 1, then only it will give 90, otherwise 45 degree, if it is 0.5, it is 0.2, so you will get different phase angles. So that is one way from experiment actually we have come to this conclusion that this is the fractional order element. Now at the initial phase actually we have deep capacitive type probe. You can see this is the probe that we make PCB, that for the circuit. That PCB is actually double-sided copper cladded PCB, and that we have coated with some polymers, and that coating we can actually modulate. We can make different coating so that we can get different values of this alpha. So when we dip inside any ionic media, we have seen that it is exhibiting different actually phase angles. So at the beginning we had these buffer solutions of phase 4, 7 and 9, and we have seen we are getting different phase angles. For see here we are getting 10 degree, here we are getting something around 32 degree, and it was something around 47 degree. So for different pH each value, it is showing a constant phase. That means they are different constant phase elements. Now, let me ask you the question. From here, can you get the hint how it can become a sensor? Suppose I don't know which one is page 4, which is page 7, which one is page 9. I have been given a unknown solution. So I dip my probe, I get a phase angle, then I try to see that whether it is actually minus 45, minus 32 or not. Then we can say that is the actually the pH of that solution. So it's a sensing it is doing. And if it is something in between, then also you can say no, the pH is actually something in. So it's itself in its property, you can see the sensing is there. We can sense different ionic concentration. So, the question comes that why actually, if you dip the probe inside the let's see, I have I think 8. Just let me, I'll show you. I have a without putting a dip inside a polarizable medium, to this, so then it does not, it behaves like a capacitor. But when you give a coating, then actually it gives the different phase angle which is in between 90 to so we naturally, why it is becoming so? Then we have searched, we have taken the surface photograph, SCM, with the SCM machine. So that this we have seen when it has been gone to the micron level, then we have seen there are many pores that is being formed on the plate of the capacitor. Previously, without the putting, it was like this, just copper, because the surface is not smooth in the micron level. That is, of course, to show like this. But see here, it is actually different pores are being formed. And then we have again searched literature. We have seen that in chemical engineering there is a concept that is called anomalous diffusion. Okay, so when there is a equal to some r to the power gamma, and the or t rather, that t is actually integer. But when there is an anomalous diffusion, that means the mean free path of the ions which are diffusing are not same. It's a distributed. It has a distributed time constant. That means one ion is going in, suppose 1 second, another one is going in 1.2 seconds, another one is going in 2 seconds, another is going in 1.1 second, another one is 0.5 seconds. So if you accumulate the whole behavior, then actually it can be represented by a fractional order differential equation. So it is already there in the nature, in the distribution column, in the distillation column, always actually we find this behavior. So that is the reason actually when we have coated it with a polymer which gives this force, then actually this gives you the fractional behavior. So if you see in literature, many people call it a fractance, that means capacitance and fractional. many people call the fractal resistor and the fractional combination. We call it fractional order element. It looks like more general. In the electrochemistry, even in 1940s, when the electrochemist has first observed this behavior, because they were researching with the battery life, and they found that there is some behavior which is not, they cannot explain with the equation by which these kinetic equations and all. Then they have, and they are actually how this battery research goes on. They try to make an electrical equivalent circuit of it. In the electrical domain, they are saying no circuit element can be actually fitting it. So then they give him the term there is a constant phase element. So in that sense, a resistor is also a constant phase element, a capacitor is also a constant phase element, because the capacitor gives a minus 90 degree constant phase. Inductor gives plus 90 degree constant phase. So all of them are constant phase elements. The electrochemist gives this element, and I don't know from where this word book element, this terminology has come, but random circuit, Randall's was a chemist, so he has, for all battery research, on the surface of the electrode what is happening, so he made it an element put there, and it's called a worm element. So we have made like this, so we can change this Q and alpha according to our actually behavior. Actually, I had a very, I would say, encouraging experience. Once I went to Italy for some giving a talk on this similar type of workshop. But that time parallelly in some other building, so there was a conference going on. And there one professor whom I did not know, he was showing this fractional element, and he was showing that in India, IIT Kharagpur, Karabi Biswas has made such an element which actually can give you different values of alpha and Q, and that is the first actually the concept came by modulating the dielectric property, you can get different values of alpha and Q. So when you get such a feedback, suddenly actually it lifts your confidence. So that also happened with me. Actually, this previously people used to try to make different fractional element, but all were actually trying to do it with the 0.5 lambda, or they are trying to make it with resistors and capacitors with the parallel circuits, because Heaviside, he found that in the power distribution line, if you just there are so many parallel resistors and capacitor, infinite transmission line. If you take its impedance, it is nothing but Z equal to Q raised to the power minus 0.5. So people are also trying to make that 0.5, but this observation, importance of this observation is that it can be also, you can modulate the material property, that means the coating of the material and also the polarizable medium, and you can get different fractional elements, different value of Q and alpha. So, and as I am an instrumentation engineer basically, so I thought that why can't I use it as a sensor? So actually on weekend I was just doing wild experiment when my guide was away, so I put inside the milk, and then I went home, then there was a data logger, then after 6 hours as I came back, I saw that the phase angle has actually changed to some other value. And then I saw, okay, so I can sense the beverage quality also. So when the milk has deteriorated, some ionic property has changed, then actually it is showing different behavior. So that's how actually, that's why this I was, at the beginning I said the milk adulteration detector, actually 2 of my PhD students have done PhD on that. And also we are now trying to develop a mastitis detector, that is a disease in cow. So that is actually how we are trying to make this as a sensor. So why actually here actually this, we are not so much concentrating on the Z. Z, that means here Z is not that magnitude. We have seen that if I can measure the phase angles, that give me certain advantage in the signal conditioning circuits. Phase angle measurement circuit is much simpler. And we have seen that this phase angle is a function of the coating thickness, the area, how much I am dipping in, and the ionic property of the medium. That means if I fix the coating thickness and the area, then it will be able to measure the ionic concentration. Now you know that this milk, when it spoils, it becomes different ionic, it becomes sour. So similarly the beverages, it also behaves like that, right? So we just try to make that one as a sensor. So we have experimented lots with this. So this already you have seen with the pH. Here it is showing with different KCl solutions. And you can see at some frequency, if we see that the phase angles are actually different. Because when you are sensing, then your circuit you are fixing to a particular frequency. And if in that frequency I get different phase angles for different ionic medium, then that is my purpose is served. I get the sensing property. So that we have seen that it behaves differently. See here the phase angles are different, and with that we have just made a very simple, this circuit is a standard literature circuit. This is standard circuit available in the literature. So here we have this sensor and here is a resistance. So this gives me, if I give a sine wave, this also sine wave, but this gives a sine wave but with the phase difference. So then we convert it to with a comparator with a square wave. So we give a phase angle. So at the beginning we used to use a XOR gate, and at the XOR gate output we get the pulses. Then again we used to convert it to resistor capacitor filter to give the DC. But now actually there itself we measure the pulse, because by this time this microcontroller has come in the market and it has become very simple to count the pulses rather than converting to the voltage and then measuring that one, right? So before using it as a sensor, so we have to be careful that actually how it behaves and the humidity, the gas sensors, the ZNO sensors. So there is a big problem of that is that with the humidity and the temperature, the behavior changes. So naturally, they actually heat that surface of that gas sensors so that they can detect the concentration of gases. So naturally, when we have proposed it as a sensor, naturally people have questioned us how does it behave in different humidity and different temperatures. So here is say, so we have taken from 40 to 70% of humidity, and we have taken different phase and different frequencies. And you can see this is minus 89 and this is minus 89.2. So this is actually the same. So that one, if I connect both, so we have seen that with the humidity, it almost constant. It does not change the phase again. So that means humidity is not my concern. In any humid condition, I can use it as a sensor. Similarly, we have also done the temperature thing. And here also again you see this is starting from some 80.8, that means it's almost 89, near about 89, and it is 89.2. So you can also see that that change is really very small with the temperature as well. So every sensor have that tolerance. We cannot say that it will be a flat. So but we can assure that if it does not have much change in the with this humidity and the temperature change. So with this actually we went for microbial reaction. So we take a break at 3:50 at what time? 3:50. Okay. So we have trying to do this batch yeast culture and detection of spoilage of milk. Again, actually this I did during my PhD time. So what we did, this is an setup. So actually here this actually is my culture media. Here is the probe inside it. So we have excited with the this signal generator at a particular frequency. So simultaneously I was seeing the phase angle over here, and through the data level I was collecting the phase amplitude and phase data, right? So that's how the experimental show up. And in yeast culture, what we have seen that this is actually how it behaves. So this is the in literature for yeast culture. This first actually with the concept, this is in time, that means from 0 to 20 hours. If I culture the yeast, there is a standard protocol to culture the yeast. I have to put it in an incubator, then I have to shake it. So for 20 hours continuously, then what happens at the beginning when yeast actually try to germinate or what it calls grow, then actually this curve, growing curve looks like this, and after that it flattens. And that actually, as I was doing with the circuit, so there was I was measuring that due to this change in this cell concentration, how my voltage is changing. So cell concentration, so you see these two curves are almost similar, only it is inverted. Inverted because actually I have taken that my op-amp, output op-amp was an inverting op-amp. That's why otherwise it's almost the similar type of curve I got it. And the spoilage of raw milk that I said. So we have in literature it has been shown that actually when you keep the milk, there are different types of microbial element that grows slowly. That is Streptococcus, Lactobacilli, then yeast, then this Pseudomonas spectropharmus. So all of their growth curve is something like that with time. That means at different hours they grows like this. And if you cumulatively, if you take their pH value, it looks like this, right? So here also if you see, our output voltage is also, maybe this shape is a ideal one. We are getting in phase 1, phase 2, phase 3, phase 4 like this. So why it saturates, that came to our minds after some time, why the pH gets saturated. So then this biotechnological, they said actually at the beginning there is this growing curves. Then after that when they die down, then because you are giving food to this culture medium, so they eats that food. So after that when, and this ionic concentration is because they excrete their from their body, so that changes the ionic property of the medium. And then after some time, when the food and the oxygen of this culture medium gets exhausted, then they die down. That time it becomes flat. So this has been actually rectified by the biotechnologist. Yes, this comes like that. We have also seen that in the literature. So this gives actually, it's a very simple sensor, but what you have to do a culture, because when it may not give the exact same count, but it gives you the behavior. So that means, and this sensor you see, it is a rigid type sensor, can be deep inside the medium, and then you can do all experiment. So that actually an advantage is, if we don't have to take out at a different hour and then the culture, then look under the microscope to find its, how much has the growth, how is the growth curve, right? So you can do it. And if you make it this ion selective membrane on this sensor, then maybe you can also able to find that these curves as well. So if you can an ion selective membrane, which is only this Streptococcus lactis, it will only capture, then others will not come. So at the beginning hour, whether it is being developed or not, that you can find. So if I extend this sensing behavior, suppose in Midnapur district, every year there is a flood, right? So at that time actually that diarrhea and this type of disease, waterborne disease, is a big problem. So if you have such a small sensor, affordable sensors to the users, to the household, they can easily see whether there is some this type of this harmful microbial content is there in the water or not. Then you can drink accordingly that. So that makes it as a good sensing property. So so we can say that in the performance of sensor in microbial reaction, that is the metabolic activity of microorganisms transforms low conductive substrate or nutrients into high conductive components. That has been actually told by the biotechnologist to me. And the phase angle of the constructed CPU will change with the change in the ionic concentration of the culture medium arising from the metabolic activity. Because when this microbial organisms develop, they have the metabolic activity, and that changes the ionic concentration. And the phase angle introduced by the sensor is measured, and it was a new concept in impedance measuring. And we have found that phase detection mechanism is actually much simpler than the impedance measuring mechanism, the J, if we want to measure the complete J or only R or only C. So then actually when I was in Durgapur, just after, actually when I was in Durgapur, that time I was doing, taking study, I came for doing the PhD in Kharagpur. So that time I had a PhD scholar, so she worked on this milk adaptation. So one of the, this Horingata, one of the scientists from Horingata milk, this organization, he said, that we have a great big problem with the synthetic milk. I said, what is that? They said, that in Bengal we call that chana, right? So from which we are very fond of mishti chana. So, they said how people make that chana, they use nitric acid, which we use for our cleaning our toilets, because that is cheaper. Now, that chana jal, that water, and next time when they want to make this chana, then again they use that water. So that you don't have to. So what is happening? So in that chana you have a content of nitric acid, and also in that chana jal also that is there. So that is recycling going on. And then then there is a lactometer which can measure the specific gravity of the milk and can tell that whether you have water you have actually active. They say not only that make the chana with this nitric acid and that chana jal which is in the milk, right? And because if we add it in the milk, what will happen is acidic, so it will curdle the. So to neutralize that, they put some NaOH. So your pH is retained, and if you add a little bit of NaOH, then your shelf life goes up. That means that milk will not spoil for a longer time. So that is actually synthetic milk. So this is not only the one type of synthetic milk, the other type of synthetic milk is, I think now in many YouTube videos and you can see, they just put 1 to 3 drops of vegetable oil and that vegetable oil in water, and that actually does not mix with water, oil, so they put some detergent. And at that time it actually gets mixed up. Not only that, they use some whitener also, and it gives some foamy type of surface at the top. So they show that, see, this is just now I have bought this milk, fresh milk to you, which still has the foam, but that is still not the milk at all. That is synthetic milk, and that is being actually, that is the proof is that in India the amount of milk produced and the amount of milk consumed is much higher. So that is a proof that there are lots of synthetic milk is being produced. Okay.
From synthetic milk, chana can be made?
No. That's why they use to make the chana, that thing.
No, I'm sure that I take milk actually from somebody, and every day I make chana.
No, that will not make chana because that lactose contains, right? So that will not be. But if I suppose 2 liters of milk, 2 liters of milk, if they put 500 liters of synthetic milk, you don't know. So that day this maybe cow has actually has a different lactation stage, that's why you are getting less chana. You will think like that. But that is a rampant practice. So all people do that only. Only the synthetic milk this amount.
গরু পোষো দুধ গরু পালন করো তবে দুধ
So thinking that, so this I had also a very good experience. So actually that's why I avoid all milk products mostly. Don't take it away. Anyway, so you know when we have sent this paper,
What about the packaged milk?
actually packaged milk is better in the sense that there is some quality control is being done. Though we think that the people who are bringing, if he is honest or she is honest, will get the thing. But you don't know. And what actually compel her to dishonesty, that also we are not in a position to judge. He needs some more money, so he can make a dish. So you cannot say that these all are dishonest people. So maybe he is compelled to do that dishonesty. But when it is packet milk, the company actually has to do some quality control. Otherwise, they have always competitor in the market. They will get caught. But there is always a risk with the milk which are actually available in this we take from the farmers. Okay. So now, what are you saying? That when we send this paper, then you know the reviewer and editor said, no, this paper it is only the problem of this maybe your country. This is not a problem of most of the country here. No milk. Then actually my research scholar Shivli and I found out in 1923 in Lancet, that is in UK, they also actually reported about this adulteration of milk with not the synthetic milk but with water and all. So then we have written the rebuttal. You see, it is not in India. It was there in UK that time, and it is also in most of the developing countries. This is a problem. They accepted our paper, but first they commented that okay, in India you were doing this of practice and all, but that's in 1923 it was reported in Lancet in UK. So that's there, okay. So she actually did these 30% whey, 20% tap water, so all sort of mixing how to make the synthetic milk, and she has found that actually when you are using urea, when tap water, then actually you are getting different phase angle. And she also come up with the conclusion, see, when you are using tap water, you are getting phase angle in some band, when you are using whey in some band, when you urea some band. So you said that my single sensor can act as a sensor array as well. If you get in the band of, suppose this frequency, I am doing in this frequency, suppose this is 5 kilohertz, I get something around 15 degrees, so I will say the tap water adulteration is there. If I get something around 12 degree or 11 degree, then I will say, okay, this is whey adulteration, because she has made with the whey milk plus this 50% whey, 20% whey. Then people also use the urea also, actually to increase the density of the milk, because the lactometer and all that, they measure the density to say that whether it is water has been added or not, right? So all sorts of practices goes on. So, no, but if you think you can, then you can eat anything, even the fruits, the fresh fruits, they are also actually contaminated with so many things. Anyway, but the takeaway is actually to the farmers, we have to give the affordable sensors. Otherwise, it's not only actually from their from their product, if they don't get their livelihood, then they will do this practice. You cannot stop it. And the government has to do the regulatory board, functioning regulatory board. Now that all can be done if we can make the sensors which are actually affordable and which are cheap and also which can be used by the common people, not very complex. You don't have to go to the lab to read by the experienced person, right? So that's the takeaway. I take it in that way. Okay? So this is a different, as what I have said, that natural milk plus 30% of liquid plus NOH. So increase the volume, NOH is added to compensate the pH value. So, we have then as we try to is the instrumentation. Always I try to make the complete instrumentation system, the sensors, circuit, and the display. So the output voltage also we have noted down, and we have seen that for the different solutions, actually we will get different output voltages. From where you can draw the calibration curve and you can come to a conclusion. So this is actually the calibration curve, which is of course it may not be always linear. So the synthetic milk lies here, lives here, the pure milk lives here. The output voltage is around almost 0.5 volt is 500 millivolt is a quite big voltage for detection, right? So also in the tabular form we have seen that for the different milk, how the different voltages coming in. So then with that we tried that whether we can make that milk analyzer. Here actually I have a very bad experience.
Can you please go back to the previous?
Yes, yes.
Horizontal into and output. Okay. Another one was frequency versus output voltage.
This one.
Output voltage and frequency.
Frequency.
And another one is output voltage versus.
So in this case we have taken a particular frequency. Oh, that frequency is not mentioned, that is made the confusion. So in this curve, I think they have taken selected a frequency over here, right? Some 17 kilohertz. So then if you plot in that particular frequency, phase angle versus output voltage, because when you are making a sensing circuit, the frequency has to be fixed. So from this above curve, we will see that which frequency I have maximum deviation. I can also take 15 kilohertz, right? If I find that as the maximum deviation between two consecutive values. So it can be different for you also, but that's actually how the methodology, which methodology we have adopted, that we have shown. We have drawn the frequency response, then from there we have taken a particular frequency, and at that frequency we have made the signal conditioning circuit so that I get that. So then just I'll why we went for milk analyzer and what is our experience. So after I am not very like going to different company and I have made this product and all. I am not that sort of a person. So but these two company from Gujarat as well as the Bosch from Bangalore, they came to our lab and they said that we have read your paper, we are interested to take your technology, and we are very happy that okay they will take our technology so much. Then in Bosch, one of my students went, she remained and she given them the prototype, and they have examined that they have an NIR spectroscopy meter which can measure the NaCl content in milk, and they have also written the mail, that mails are with me, that that 13 lakh rupees NIR spectrometer, which the resolution of that is actually our meter, which is cost hardly 1,500 or 2,000. That is better, giving better resolution than that machine. But then Bosch was some days actually interested, but after some time actually our country is not very manufacturer friendly. Now Bosch, they have again shifted to the software and solutions, and they said, sorry, we are not continuing in this domain. But Gujarat is the milk, and they have Anand, they have different group. They came and then they said, look, you have done adulteration detection, that is very good, but we are not interested in this adulteration detection. I said, why? Because these buyers are not interested in that. What we are interested is that what is the fat and SNF ratio in my milk. But Sally, you have asked that with that milk, the chana will come out. So that fat SNF ratio tells you that how much chana you can produce, right? So if your fat SNF ratio, that SNF ratio is more or fat is more, according to that they pay the farmer.
Nice.
Okay. So they said we are not interested at all in the adulteration. We are interested milk and milk analyzer, we get the fat SNF ratio. And now also, till now, also they do buy, and which comes from the Bulgaria, which is actually, what does it do? Through a small channel, they pass the milk, and there is an ultrasonic sensor which actually measures the density of milk. And from that density, they produce the calibration curve, the fat and SNF. So I questioned them that then you are, every time you are not cleaning, even if you are cleaning, the ultrasonic sensors, how can you say that every time it is actually measuring faithfully? So you are actually maybe making wrong measurement. It only depends upon how clean is your through. This is the first measurement, milk going through a very narrow, I think 2 millimeter narrow this pipe. So otherwise the ultrasonic sensors, actually the receiver and transmitter, that strength, that actually not very useful. So, but you were saying that you are cleaning it, but every time you are not cleaning, next time, suppose one milk has gone with high fat, next milk low fat, it may show in between. So how do you know? That also we are not interested. We show the display comes, we show the farmers, they get the money, they go, okay. So the problem of technology is this, that it is actually who understand how. So to them also I have given a prototype. Then they said they have measured. They said, see, because we have to work in lab only. So we have done mostly 20 in our 25 to 30 maximum in our lab temperature values. In Gujarat, maybe they have measured in something 40 degrees. So then now what is your calibration curve? With that, this is not matching. So I said, okay, give me the feedback so that I can modify, I can do a calibration. They said, no, we want product, we don't want research. I said, okay, then thank you. How can I can make a product which I don't know in an unknown environment how it will work. So I think after the tea break I will continue with this. So I don't have much more to say. So how this is going on. which can give you the solid, not fat. And this solid, not fat, is, we have seen literature, what they actually use the equation is this, that fat person, they multiply, this is an empirical relationship with many experiments, people have developed this, and then this value of what is the estimated %, on the basis of that, actually the buyer gives the price to the farmer. So I say to my scholar again, let's explore this, whether we can do. Then she has found that actually for cow milk, lactose, salts, protein, we have to multiply by these elements. This is available in literature. Those who do their research in this milk and this agriculture sector, this is standard equation they use there. So what we did now, so on this sensor, we have given a lipase protein. Lipase, you know, that when our blood has triglyceride, right? So how this is being detected? This is being detected actually in another enzyme which can actually bind that triglyceride, and from there this machine gives you that percentage. So we have found that if I want to measure the fat percent, then this lipase we need to actually use as a binder to bind the fat. So what we actually, our sensor making process is very simple. We make the PMMA solution. So in that we have actually also this lipase powder. We have mixed it and then made this. See, this was the previous sensor, only PMMA powder, and this something is like lipase plus PMMA protein. So this type of sensors we have made, and then again all characterization, you have to again do frequency characterization, everything, and we have seen that when water is added, the fat content naturally goes down, the conductivity goes down, and as our measuring, because we convert it in the electrical, so phase angle goes down. So we have seen that this is the conductivity versus this phase angle versus the conductivity curve that we get. So this you see that for the different percentage of fat, this is actually different phase angles that has been we measure it by the instrument. So she has actually made a small handheld type instrument with that, and this is on the PCB board. She has with an Arduino which can be display this giving in the milk. This is the sensor, and we can actually get the milk. Now they said I want a milk analyzer, so no, I said okay, we can make that as well. So now ultimately we have packaged it in like this, and this is also being demonstrated in Maharashtra, in front of Maharashtra government, and also the Melissa scholar, she has also got this Gandhi Innovation Award because of this development. So now again our question comes, when we approach the funding agency like DST or might be that you want to make this prototype and go for commercialization and give us money. Then there is the story. They have already given a huge amount of money to the Siri Pillani to develop the instrument, who has developed a key scanner, basic. Okay, the name they have given, and so this government agency also, they don't want to make any more another adulteration detection. Though we have searched many times for the clear scanner in the market, that is not available, but Rajasthan's India Limited, they have taken that concept and trying to make different this milk quality instrument on that. So, but our instrument still works fine. This was for more than 2 years, was in India like Ullani, and we have tested that this when it is fat percentage, they have an milk-phos from Denmark, most probably. That instrument they use for their cattle yard. They have a 70 different breed of cows. So we said that let us validate our instrument. So we have validated our instrument in India Kolani, and we have seen that whatever that milk-phos, this instrument is at par to them. Only difference is our thing still cannot detect urea and water. Apart from that, the salt, in a way, synthetic milk, all the other things this can detect. And the second thing where we have actually lacking, they take only 30 seconds, where for single testing we need 2 minutes. That is actually 2 drawbacks we have from that instrument. And again I will say this hardly cost, this bill of material cost is maybe in a packaged one is 2,500 or 3,000, but that milk-phos cost 6 lakhs. You have to buy it from Denmark. So if some actually entrepreneur or someone wants to take the technology, that is very good for us. It is already built and already been tested with 2 research scholars has worked on these sensors and this signal conditioning sensor. And this is my research scholar who had actually, he has said that it's INR 10,000 without heating. Actually, she also had made a heating system in that, because she has found that at 42 degrees centigrade, it is the best resolution we can get. That's why she has also made a heating system, and with the heating system, she said that our cost is 10,000, and she has actually with different milk-scan, lactoscan, lactoscope. So this is by Delta instrument, this is by Sunke Carver Germany, this is by Fossil USA. So if you this performance parameter, if you can find, they are actually doing. So when she has submitted her thesis, she did not do the SNF protein, but the next scholar, she is actually, not she now, he is actually, this SNF and protein thing is actually trying to implement in that. So this is actually the comparative table of the instrument which we have developed based on the same sensors, the same principle of the sensors. Now next we come to this mastitis disease in cow. These cows often get an infection. This is by some bacteria. The name of the bacteria is mastitis. Anyway, so what happens, I think those who have a small experience, you will see that in the udder tissues, see, in these udder tissues, they become reddish. And what happens when they get actually this disease, then actually the production of milk gets reduced. It produces less amount of milk. And after some time, actually this udder tissue, this get blocked. So it may happen that many cows, if they get this mastitis disease, which is due to some bacterial infection, because they sit on the ground and not very hygienic way they are actually hard in the field, and also this is very common disease, and we have actually this is a big problem, and research has shown that per cow, if we have this mastitis disease, then actually 47,000 loss in a year per cow. So suppose a milk, a farmer or in a milk farming this year, there are 100 cows, so you can 47,000 multiplied by 100. That is the net loss because of reduced amount of milk that is being produced. Now the thing is here that you have to get this disease in subclinical stage. That means when it is just started growing the infection. So how do they do actually? There is a somatic cell counter. What happens when cow gets this disease, then in the milk the somatic cell that counts get high. Now there is an instrument which actually can measure the subclinical mastitis. So if you can identify or detect within 1.5 lakh, then actually if you can treat them that time, then that is the cow is cured. Then comes the next stage, the clinical mastitis, then the very recurrent clinical mastitis. And sometimes when this recurrent clinical mastitis happens, the cow may also die. So that's a huge loss to the farmers. So this is some experienced eyes that is being used by in a household, but in India, Kolani, or in all over the world, what people do, this is called the California mastitis test. That means there is an chemical, again the full name of the chemical. So there is actually, this is in the from the 4 udder, they collect the milk in the 4 one, and there is a handle. Then they put this chemical. Then what happens? If that forms a gel, then you say there is a mastitis. So by that actually they try to identify that in a cow which one actually has got the mastitis. So that is a universal test people try to do. Now problem is, to a farmer, it is this putting this chemical, and this chemical is costly. Even in India, when we say that when we are validating our instrument, for every cow you do CMT, they say when the professor is there, he uses it generously. But when the lab assistant is there, he or she tries to give a less amount of the which is required. If less amount is given, it may happen that subclinical mastitis, the gel may not form. So then actually it has a disease, but you are not able to identify. So it is an human error also may happen. So rather, whether an electronic thing can be done. So there is a somatic cell counter in India, Kullami, where actually there is a cassette they put inside, and again that actually counts the somatic cell, and that takes more time. I think for one it takes 15 minutes or so, one sample. Okay, and that cassette, one cassette costs 300 rupees. So that is also not affordable by any farmer. Even the Indian Kullan, they are also saying for calibrating your instrument, now you have to supply us cassette, because so we don't have that much of fund. So this is a problem of research in our country, of course. So what we are trying to do, that as you have seen, the adulteration, government is not interested, companies are not interested, if government has given money to some other organization, they won't let that organization come up with the product. Why again I will give funding to other institute? So, but actually, you know, those who actually produce manufactures the countries, they always look for 5-6 different solutions. Among them, which one is the best, that they promote. Even in the semiconductor industry also, for the same problem, come up with different solutions. So that is, we have a different outlook. We think that, okay, he is or she is doing this problem, let her come up with some solution. But it never, the one solution never actually solves the problem. I can give you an example. We think that MIT is a big institute and all, they have all this research. You know how much percentage of the research is actually goes to the market? Guess?
0.9.
0.9. Then? Anyone else? 1%. 5%. 0.5. So you are more realistic. Actually, the same question, a professor from Georgia Tech, who is now heading this ISM India Semiconductor Mission, Professor Rao Tumalla, he came to IIT Kharagpur. When he asked our professors, people started, oh, MIT, 50%, 30%, 20%. No, it's only 3%. Okay, so 3%. So whatever research they are doing, they are top researchers of the world, we say, but they are, from their research, only 3% is actually counts as a product. So if we think that we have given some 10 lakh, 20 lakh, 30 lakh, so that will produce a manufacturing sector, that is not actually possible. That maybe we are that's why behind. So as this, when I actually make this as an adulteration detector, then MIT denied to give the money. Then SIDA Kolkata has advised me, can you just improvise it and make some other products? I said, okay, so I have seen this mastitis, let us then check whether it can detect the mastitis. So I and my student in India, Karabi, actually was doing with that same, because I have got 70 different cows. That is a big input to me, because in Kharagpur I get so many different breed of cows to test samples. So then we said, okay, which has mastitis, bring that way. And immediately our machine detected that, given the different phase angle and different voltage. Then we said, yes, we can measure. So now we are actually making a mastitis detector. Hopefully, I am hopeful that at least one instrument will see the light in the market. So here our objective is that in the field level, if we can measure, that means we will give it to the farmer, they will make the test. So this, now at the beginning we take the milk sample, mastitis detector, that is the name of our instrument, and we do California test and somatic cell counting in the NDRI colony. Then we make the comparison and come to the conclusion that and we try to, actually every instrument needs the calibration, right? So that calibration we try to do. So this measuring circuit and all is same. It is displayed in this LCD. So we have ultimately come up with an company in Kolkata, Code Technologies. So we have made this handler, and now actually this is in the field in NDRI Kollani. So we have said that whichever one is actually you are getting this, just suspecting that it has getting mastitis, that samples you test with our instrument so that we can understand that which level we have to make the calibration so that we can get the subclinical mastitis to be detected. Because if it goes to the clinical mastitis or critical clinical mastitis, then actually it is not reversible. But if you start treating in subclinical mastitis, then it is curable and you get less amount of loss, that I can say. So, okay, so this is what we are developing. So should I continue? Actually, we are developing a conductivity meter that is a little different from that. Rather, you can ask me question. I can continue if you like. You can ask me question. Let me complete this sensing thing. Then we have also developed a conductivity meter. On that I will go. Same principle, same circuit. But first let me take some questions from you. If you have any query, if you want to ask something. No?
This instrument is available in Kallani, madam?
This is now going this field testing in Kollani, NDRI Kollani. So yesterday also other professors said that I have got an MTech student. Can you give me one more this one? But thing is that we had two. One always we keep in our lab for our research thing, right? Because anything they report from there we try to do it. So we are trying to make 5 clone of this so that we can give 2-3 to NDRI and some other organizations so that they can test.
The main test madam দেখেছি কিন্তু
এটা কোথায়?
হ্যাঁ মানে এই ধরনের নয় মানে অ্যাকচুয়ালি আমাদের মানে অনেক ঘাটা আছে তো তো সেখানে দুধগুলো সব এক জায়গায় জড়ো আছে তো ওনার একটা বড় গাড়ি নিয়ে আসে যেখানে মিনিটটা নেয় ওরা টেস্টিং মেশিন নিয়ে টেস্ট করে না কতটা জল আছে সেই হিসেবে রেট করে
এটা তো ল্যাক্টোমিটার।
Density measure.
সেটা হচ্ছে ডেনসিটি জল। This bill of material cost is something around 2,500 really, but actually I do not understand the business part of it. So the company which will take over it, how? So because if I now go it for suppose technology transfer, so actually from my institute will ask take some money because I have used their facility and it is their name will be. So this SIDAC Kolkata, NDRI Kollani, they are also a partner because they have facilitated this thing. So they have some stake. Then the company who is building it, they said that we can make the instrument, but we are not going to sell it. Because that so if someone wants to sell it in the market, then you can contact me. I can, to the company who is developing it, can have a meeting and that will be, because we wanted it to be to the farmers. So cost, how it is being calculated actually am very poor in that one. But bill of material cost is within 5,000, I can tell you, because you have a microcontroller, you have some circuit element, you have sensors, and you have to make this enclosure, and this is an LCD display. So we are trying to reduce the cost of OLED display we are trying to do. So these things we are trying to do. Ultimately to the farmers, maybe no display will be there, the red or green to LED will be there. But for our research, we need the displays. We see the voltage, we see the temperature, because later on we use that for calibration, right? So the developing stage, that all costs. The bill of material cost is not that, and these sensors are in-house made sensors. So they are not also very costly to do. So, but if someone of you know some person who are interested to sell this in the market, yeah.
Madam, can you repeat that question in the back side? How the fractional order is work as an electrochemical sensor in an analytical part?
Analytical part. Okay. Let me. So I have a sense capacitor sensor. So this is a sensor you have seen. This is a copper electrode. This is a copper electrode, and this is epoxy glass inside, or you can say it's a polymer, right? So what do you know? We connect to from here to this is electrical connection.
Voltage.
Electrical connection. No. So this is first. If you have seen this, we have to, yes, here you see. So you can see this. This is this impedance analyzer or LCR meter. So these are the two electrodes, right? This is one red and one green. So this we have put. So what this instrument does, it gives an here we connect one signal generator which produces 1 volt peak to peak sinusoid. Okay. So this is being applied to it.
1 volt.
Yes, only 1 volt. It can also work at 0.5 volts also. Right? Now this is when we make this. So this is nothing but a capacitor C equal to epsilon 0 epsilon r A by D. So D is this and A is the area, right? Fine. Now I have D inside a polarizable media. Before that, what is happening? If this is my positive side, this is my negative side, my field lines are going into this. And from there, we deduce this parallel plate capacitance equation. Right? Now, when I do like this, in addition to this, there are actually many field lines flow through this.
Yes, ma'am.
So that means this becomes C, I say epoxy, plus I can say the C liquid. So then also no problem. I have only two capacitors, they are in parallel, they will add up. But here is the difference. This any metal and electrolyte interface, this is not a typical this only field lines it is being generated. There are many layers are formed. we have first the Helmholtz layer, then we have Stern layer, that Helmholtz-Stern layer. So what are they? There is actually charge transfer takes place. That means some of the charges actually from these try to diffuse into here. Okay? Some of them tries to comes in. Now we have a porous of different this in micron level. I have shown you, I think. We have different porous material. So this is the surface of it, right? So when these ions from here try to diffuse in, then actually this mean free path of this diffusion is no more this mean free path of diffusion that is given by the R is no more actually proportional to the time constant of the ions. It actually, this is for regular diffusion. And this R that is T to the power alpha, this we call the anomalous diffusion. Okay. So when we have these pores of different size, now we had also studied that how much time you should dip in, how much will be your this concentration of the liquid in which I am putting first probe. So all that actually defines my this alpha. Okay, this alpha is a fraction. So when there is an anomalous diffusion, this we will see in chemistry and chemical engineering, in distribution column or distillation column. This is very prevalent. So they call it an anomalous diffusion. Then alpha is no more a integer, it is a fraction. So that is happened because these ions which are trying to diffuse in, someone may try to diffuse and go to the surface. Someone at all may not go. There are some charge transfer occurs at the surface. There may be a small layer of this positive negative charge accumulation on this surface. So all of them, when I am measuring at this 2n, all of them together giving me a impedance which is z equal to q s to the power minus alpha, where alpha is a fraction. And I can change this q and alpha because that is doing many experiments. We have come up with the point that how much you should proceed so that you can get this different pore size, and which pore size will result what alpha, what q, that also we understand. Okay, so that behind physics is this thing. So once we have got this, actually we are no more interested with the internally what is happening to it. We are interested to get different alpha value for different concentration of this ionic media. In that time, this circuit actually becomes maybe like this. There is an CP element, there is capacitance, maybe there is one more resistance here. So different configure. There may be one more resistance here. So famous Randall circuit is like this. So this is called Randall circuit. So who say that if you dip a metal, these electrodes inside any ionic media, there will be a hook element, and this called the charge transfer resistance. So charge transfer resistance, why? Because some ions are trying to go inside, come out. So naturally that will produce a resistance. So he represented it like this. There is some ions will just line up and stand over there, and they are very nano level of layers. If you see in chemistry, it is called Helmholtz layer, Stern layer, then Guy-Helmholtz layer. There are different layers are formed. So for that, we the electrical engineers try to model it with the circuit elements. That's all. So our circuit element is this one, okay, and this circuit element may not be this much simple, maybe it has many more resistance, capacitance, they are combined. But because of this mean free path distribution, they are always actually give you this fraction. That's why heavy side, who actually was trying to measure the impedance of the power transmission line. So when he made the infinite power transmission line, this resistance, capacitance, I think is like this. So he tries to make infinite transmission line, power transmission line, and then he deducted the formula that for this impedance equal to Z equal to Q is a constant S to the power minus 0.5. This is heavy side, has found it 1923. So this is also the same thing. That means when there is a distributed thing, then actually we get this type of behavior. That's why actually we say that when you have a network, nowadays this with AI, with network, with the sensor network, people say actually you have to use this some sort of fractional calculus to get the true behavior, how you will behave in network. That's why actually in the soft robots there are infinite number of joints. Suppose a soft robot which is like a lizard. So there is a fire in this room. So human don't want to come in, but through the lizard you want to push some chemical so that the fire get extinguished. So how if you want to through a small hole, you want to pass this lizard to this room, then you have to control its path track its path very minutely. In that case actually they say that you have to use the fractional calculus. So anything which is actually distributed in nature, that actually gives you this alpha, not a constant but a fraction. So that is first the chemist.
Less than 1.
Huh?
Fraction is always less than 1.
Now as an I can say it is less than 1 for the simple element and all, but nowadays for the controllers and other purpose people are using, for the element of course it is less than 1, but for controller design and all it is 1.5, 2.5, it can be anything. Like if you want to make Chebyshev filter and all, you know that the filter, what we do, if we get for 4.2 filter, what we do? We go to the fifth order filter, right? So, but if we have fractional element in hand, we can make a exactly 4.2 a 4.5 filter. So, it's not always less than 1 in not that sense, but in that the capacitor which you may use, that may have a 0.2, alpha equal to 0.2. That means the phase angle is minus 18 degree in place of minus 90 degree. Minus 90 degree is minus 1, so minus 0.2 is minus 18 degree. So you need an element which shows a minus 18 degree constant phase element in your required band while you want to operate the circuit. Okay, so it is all of them are actually analogous. In the chemical engineering, in the nature, you see in the volcano, even in the stock market. Now people are trying to use the fractional calculus because that is also, you don't know how the people will behave in that, right? They're saying that predicting the value of the stock, if you use the fractional calculus, you may predict it in a better way. So that is also being used in the stock market. In volcanology, in virus exploration, many places people are now trying to use this. Where anything is distributed, then only it is come to a
That formula will be applied. Z equal to Q.
that is for the electrical circuit element formula. For the differential equation, if you want to make, suppose this is in your differential equation. If it is in your circuit, this is a resistance and this is your Z. Okay? Fine? So suppose this is your current I. This is R. So what will be your voltage across this? So V0 equal to, if this is Vs divided by R plus Z, which is nothing but Q s to the power minus alpha multiplied by Q s to the power minus alpha, right? This is the equation. Now if you get this, then if you want to write it in the differential form, suppose V0 by Vs, then how will you write? This is Q, this s to the power alpha, how do we write?
Sign first.
Or s,
J.
in differential equation, s means d dt.
D by dt.
So here I will write d to the power minus alpha, dt to the power minus alpha. And if I, so okay, I can write it. Yeah, I am doing time domain and frequency domain. I write it here V, right? That will do R plus Q, again D minus alpha, D to the power alpha V. So if I convert it to, so that means this is fractional calculus, what I am trying to say. This is fractional calculus, right? And what we have developed is only an element, right? That element can be used to realize a fractional order system. Like in a circuit, if I want to make an filter, we use resistance capacitor.
That is helping as sensor. That is helping as sensor.
Now, a capacitor can be used as a circuit element and can also be used as a sensor. So, my fractional element can be used as a circuit element. Here, it is a circuit element. Right? Here, I am using it as a sensor because I am getting different values of alpha. I am only sensing the alpha. for sensing. For the capacitance, what we sense? The value of the magnitude of the capacitance. We assume the phase angle remains 90 degree, right? We do level measurement. When we do, right, we see the magnitude change. But here we are making the phase angle changes. So that phase angle we are measuring. When we are measuring as a sensor, that we have seen that angle theta is a function of P, A and conductivity. So that I have shown. So if this is constant, then this phase angle theta is actually the conductivity dependent. And conductivity depends upon the ionic concentration of the media. And that property we are using to make the sense. Okay. That's all. Okay, any more question? Yes? Yeah? No? Oh. So I think I should stop here. There are many ways, because when you get a new thing, you try to do it with, and we have made a conductivity meter. I said the proliferation of mammalian cell, that also we have measured. So with this, actually we are trying to develop a blood urea measuring instrument. That's milk analyzer still, though I am not getting funding, but trying to make an analyzer.
Online page.
Yes, online means, in biotechnology and all, if you go, there is always a seesaw type behavior you will see. Actually, they have to shake fish when these fish farmers are going. They just always try to do this to put the oxygen for the fish. So in any bioreactor, always that is being done automatically. Now, when they want to find out actually that they have a marker. When the pH level has grown this much, that means that time my yeast culture or bacteria culture is complete. So then they can take out that sample and again go for further research. So what they do, every 2 hours or 4 hours, they take out the sample and they measure under microscope to find that in a particular value, how many bacteria, how many yeast, etc. there. When I say online, then I say we don't have to take out and do it offline. You can insert the probe in that reactor and you can get it online. Okay, that's what I mean. Okay?
So I have a question. The literature, maximum author says that the physical realization of fractional element is much more complicated than integer element. How it is so?
Because actually, now we can, we can realize. We have realized.
It is very easy.
But this is deep inside a liquid.
Industrialization is not so much happening for fractional element.
Because actually when some industry is actually feel that this can help to growth my production or some sort profit, then only they will take the technology, right? This I have shown the sensor, but actually we have made a 1 centimeter by 1 centimeter the fractional element. So what we have done inside to plate, we have modulated the dielectric and then just tapped it. So it is just like a capacitance and that can be used in a circuit to realize. So it's difficult. That's what actually that idea came from this, that modulating the dielectric property I can change the phase again. So now, but I cannot the liquid property modulating, that is not for the circuit behavior, that is not welcome one, but that is good for sensing application. So then, and now we can, if you someday come to Kharagpur, even I think in my website, the pictures are there in my, some of my pictures, you will see it is 1 centimeter by 1 centimeter. Between two copper plate, we have made nanocomposite, which is also, it's an adhesive, so it will stick the two electrodes, and we are able to get different fraction water element. That means different value of Z and alpha. And that is a single element. That is difficult, but but commercialization of it requires much more this application. Fortunately, maybe I will be getting a project to make this in more this product form. So then maybe I'll try this. And that's why actually due to pandemic it has stopped. But before that I used to conduct workshop every year on the this fraction order element thing, so that even in that the hands-on I used to give the practice to the people how to make the fraction order capacity. That is difficult, of course difficult. And
limitation?
Huh?
Limitation?
Now the limitation is you have to compatible with the CMOS circuits. Okay, the size is still a limitation, as I don't have any access to any fab lab, right? So it is not possible for me to make a fractional capacitor which is compatible to CMOS technology. So if you cannot make a CMOS compatible, then naturally the integrated electronics people is not very welcome component to them. For the laboratory teaching, it's okay. For the pedagogy, it's okay. But ultimately, you have to go to the CMOS technology. That is the bottleneck also. But the KAUST, this King Abdullah University of Saudi Arabia, I have gone there. They have a very good lab, and there they have made the miniaturized fractional capacitor. But problem is that after that hot product, then if they make a controller, who is the buyer? And until and unless some people are convinced that it will give a edge to their industry, progress. So people will not fund you, or until you are not funded for the research, you cannot do that. So these are the limitations which we have to find. But of course, where we were in the 2002 when I started my PhD, and where it is now, it has gone a way shift. You see the paper publications, the way it is increased, and the control. You will see this year IFAC control. They have all the theme of fractional controller. So the control people are also taking it as a now the future. So okay, let us hope one day we will be able to. So with that, I thank you all. You are a very good audience. Okay. So
do you have the patent for those devices?
yes, I have got the even the patent has been published. Means patent not published means granted. I got the certificate also for the device. Not for the sensors. Sensors still the patent is pending, but
there is any possibility of commercialization of this product, commercialization?
yes, that is this master digitator is going for commercialization. They are going for commercialization. So that's what I'm saying. Actually, I have got a person, a company who said that I can make the product, but I am not going to sell it. So I need the persons who, as a professor, I said, I'm not going to that business, my own startup, and then I will be a Bengali called a Bechu Babu. I don't want to be that. So I can do the research less, other can take care of. So some people come there, if they have a knack, they make the startups go for commercialization. But I have got my junior only from IIT Kharagpur, he has a MSME company. He is actually developing that plasticity detector. But he said, Karabi, I will, as much quantity, now I understood how to make, as much quantity you want, I can make the product, but I am not going to take the responsibility of selling. So now I will tell my team that you find because it's your project, you find a company to sell it. It's not, I told them clearly, it is not my job to sell it. They try to push it, it is your job. I said, no, it's not my job to sell, you do it. Otherwise, let it be like that. Okay, any more questions? Okay, then. Thank you very much.
Thank you, ma'am, for the wonderful and informative session. Now I like to request our coordinator, Professor Sumit Banerjee sir, to give a small token of appreciation from our department.